Hey, this is Math 8, Unit 7, Lesson 15, Adding and Subtracting with Scientific Notation. So first we start off with some mental math here. Mentally decide how many non-zero digits each number is going to have. So non-zero meaning they have other digits but not the zero digits. So if I think about it, I have a 3 times 2, which gives me a 6. Everything else after that's going to be a bunch of zeros, right? So in this case here, I'm probably only going to have one non-zero digit in that problem. Okay? For this one, I have a 3 divided by 2. 3 divided by 2 gives me 1.5 at least. No matter what happens to this other stuff here, I'm going to have a bunch of zeros after that there. I'm going to end up with only 2 non-zero digits. In this case, this one here, this one's a little interesting because I have 3 times 10 to the 9th plus 2 times 10 to the 7th. Okay, so I'm still only going to have 2 non-zero digits, right? But it's going to be a little bit funkier the way it works out. Okay, because this is going to be 3 times 10 to the 9th is 9 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then 2 is 7 zeros, it's going to be somewhere about here, 1, 2, 3, 4, 5, 6, 7. So if I actually add that up, I end up with 302, and then all this mess, right? But there's still only 2. Keep that in mind though, that then if I go to this one, and I subtract, this is 300,000, 1, 2, or 3 with 9 zeros, sorry. 1, 2, 3, 1, 2, 3. And I subtract the 2, like so. When I subtract that though, what's going to happen? It's not going to be having 2, this was 2 here, because I have to borrow. And so because I'm borrowing, and then what happens is I have 10 minus 2 is 8, 9 minus 0 is 9, and 2 minus that is 2. And then we still have our 0 right here, sorry. And then 1, 2, 3, 1, 2, 3. So in this case here, I actually have 3 non-zero places or values there. So just interesting, but just kind of fun. Let's take a look at the next one. Measuring planets. Diego, Kieran, and Claire are wondering, if Neptune and Saturn were side by side, would they be wider than Jupiter? They try to add the diameters 4.7 times to the 4th and 1.2 times to the 5th. Here are the ways they approach the problem. Do you agree with any of them? Explain your reasoning. Diego says when we add the distances, we get 4.7 plus 1.2 equals 5.9. The exponent would be 9, so the two planets are 5.9 times 10 to the 9 side. Okay, that is not going to work. Okay, the reason we say no there is that while the adding part is okay, right, that's okay, what about these 10 to the 4th and 10 to the 5th? Okay, what happens with those ones there? It's just not going to become 10 to the 9th, is it? 10 to the 9th happens if you're going to be multiplying things together. So it's just not going to work out. It also is not going to work out because you can't just add those together if they have a different base. We have to change the base around. You'd have to do 4.7 times 10 to the 4th and 1.2 times 10 to the 5th. And if I want to go to make that higher, I need to move to the left. So that becomes 0.47 times 10 to the 5th. Now I can add that up and I end up with 1.67 times, and the base is the same, 10 to the 5th. A very different answer. Alright, let's look over here. It says Kieran wrote 4.7 times 10 to the 4th as 47,000. So she went 4.7 and moved the decimal over 1, 2, 3, 4 times and put the 0 space holders in. That's okay. And 1.2 times 10 to the 5th. So 1.2, and that's our 1 space holder. 1, 2, 3, 4, 5 there. And so she has 120,000. Correct, correct. She adds that up. That is correct there. So we would say yes, that is correct. That's okay. Like that. No problem. Just kind of expanded it out. Claire said, I think you can't add unless they are the same power of 10. That is a true statement. So she adds 4.7 times 10 to the fourth and 12 times 10 to the fourth to get 16.7 times 10 to the fourth. That would also be a true statement. That is a yes. When I did mine up above, I moved that one around, but she just went ahead and moved the other. She switched the 1.2 to a 12 to make it into a power of fourth. Alright, so she went to the right to make it 12, which makes that go down, and now you can add that up, no problem. So that's a great idea. Number 2, Jupiter has a diameter of 1.43 times 10 to the fifth, which is wider, Neptune and Saturn put side by side, or Jupiter? Well, that's a great question. So let's see here. If Jupiter is 1.43 and Neptune and Saturn combined we said are 1.67 times 10 to the fifth, which one's going to be larger? Well, based upon the numbers we had to work with here, they have the same bases, so we can compare this number and this number. So Jupiter is 1.43, these guys are all that, these guys are more. And that's all you gotta do. Once you have the same base, pretty easy to do. Let's flip the page, look at the next one on the celestial dance. Alright, it says, when you add the distances of Mercury, Venus, Earth, and Mars from the Sun, would you reach as far as Jupiter? Well, here's our distances of Mercury, Venus, Earth, and Mars. Okay, so first of all, let's turn this into a power of 8. So we're going to go up 1, which means what? If I'm going to go up 1, I need to go to the left and put my decimal here. Now I can add up some numbers. I have 0.579, 1.08, 1.47, and 2.28. And these are all zeros there, so we can add that up. And when I add that up, I end up with a nice big number, 9, 10, 12, 13, 14. Carry the 1, 2, 3, 4, 5. 5.409 times 10 to the 8th. And now I can compare that with the Jupiter one here. And what do we find out? We find that that one is larger, so number 1 would be no. You don't. Jupiter still wins, 7.79 compared to 5.4. It says add all the diameters of all the planets except the Sun, which is wider, all the objects or the Sun. So they want you to add all of these together and then add up the Sun. Well, it helps if you have the same base. Let's go with the 4. So I'm going to increase this. To make this go up, I need to make this go to the left, so I put my decimal there. I need this to go up to a 4, so move the decimal to the left there. I need this one to drop down, so I'm going to go down, which means decimal is going to go to the right. So now let's add the numbers up that I have. I have here a 0.4878. Here I have a 1.21, a 1.28, and then I have a 0.6785, and then this becomes a 14.28. Alright, adding these up, no problem. 8 plus 5 is 13, carry the 1, I get 16 here, carry the 1, I have 24, 32, 33, carry the 3, 7, 8, 9, 10, 11, 11 plus 8 is 19, carry the 1, and then 1, 2, 3, 4, 5, 6, 7, and a 1. Alright, so 17.9363 times 10 to the 4th is where we are right now. I'm comparing it to the Sun, which is 10 to the 6th. Let's make this go up by 2. When I go up by 2, to go up, I move this to the left 2. So 0.179363 times 10 to the 6th, comparing that to 1.392 times 10 to the 6th. And what do we find out? The Sun is still much, much bigger. Can you draw it to scale? You probably could if you wanted to. It would look something like this. There's the Sun and the planets. If that's 1, this one's going to be the planets are going to be something like this. They're doing a great job being super small. Hardly even fitting on there, if even that. Okay, I'm gonna skip the Are You Ready for More, and we're gonna go to activity 4, which is Old MacDonald's Massive Farm. Here it is. We have all these numbers here. So on a farm there was a cow, and on the farm there were 2 sheep, 3 chickens. So we have a cow, 2 sheep, 3 chickens. What's the total mass of 1 cow, 2 sheep, 3 chickens, and 1 farmer? So we're gonna add up all these fun things. So we have, in this case here, we're gonna add up one of these guys. We're gonna do 1 cow, we're gonna do 2 sheep, and we're gonna do 3 chickens, and add that up. So 1 would be 6.2 times 10 to the first. Here we have 4.0 times 10 to the second. Now I don't want to have 10 to the second, I want to keep them all the same power. So because I want that to drop down, I'm going to move this over 1 there. So make that 0.4 times 10 to the first. This can stay 6.0 times 10 to the first. And I want this to become a 0.1, so I'm going to go up by 1. So we go up, I'm going to go to the right. Right? Is that the right way to do that there? I think. Yep. This is a 1, 2. Uh-oh. Head's not working, it's getting late. Alright. Okay. Sorry, it's getting really late. Alright, backing up over here. This guy here, this cow, let's back up this sheep. Let's back this up. Back this up. It's just been split. Okay, backing up. Okay. Alright, so to make this base the same, okay, what we want to do is, I want to make this to the base, well, let's do it this way. Let's just do with whole numbers just to make it easier for you guys, okay? So, here we go. So 6.2 times 10 to the 1. This is a 6 and a 0.2. Move the decimal over here, we have 62. We have one of these guys here, right? 1 human. We have 1 cow, so this is 4 with 2 zeros, so that's going to be 400, right? 400 there. Alright, the sheep, there are 2 sheep. So this is 6 times 10 to the first, which is 60, times 2, which is 120. Okay, and 10 to the first is 1, and chickens, there were 3 chickens, so 3 times 2 equals 6. So in total we have 400, 120, 62, and 6. Alright, so that's going to be an 8, it's going to be an 8 and a 5. So total mass is 588 kilograms for what is going to be on the farm. Making a conjecture about how many ants might be on the farm. Alright, so here's the ants. We don't really know. We could say maybe there are 1 million ants. 1 million ants, maybe. If you added all these ants in the previous question, how would that affect your answer of total mass animals? So 10 to the 6, if we take 10 to the 6, or 1 times 10 to the 6, and we add that together with the number of ants that there are, 5 times 10, oh, well, actually, well, yeah. Yeah, okay. So let's just say there's 1 million ants on this farm. And we're going to say that we take their weight, which is going to be, in this case here, 3 times 10 to the negative 6. Okay, now 1 times 3 is 3, 10 to the negative 6, and this becomes 6, and we're going to add those up there. 6 plus Negative 6 is 0, so 3 times 10 to the 0 power, which is 1, equals 3. So we'd be adding about 3 kilograms to our total. So 3 plus the 588 that we had before would put us at 591, so not a very large increase at all. Okay, what's the total mass of a human, a blue whale, and 6 ants all together? Okay, so the human, we said before, was already 62. That we'd covered. A blue whale is sitting here at the mass of blue whale. We're going to go 1, and we're going to go 9, and we're going to go 1, 2, 3, 4, 5 to put our placeholders there. So blue whale is about 190,000. And then 6 ants. Now an ant is sitting here at 3 times a negative 6, right? So we're going to put a 3, and for this one here, 3, and we're going to have that's our space, 1, 2, 3, 4, 5, and 6. And so we're looking like that, but there are 6 of them, so 6 times 3 is 18. So we end up with point, in this case here, 1, 2, 3, 4, and an 18. When I add all that up, I have a really goofy number, which is 190,062.123,418. That's a really long and really goofy number, but that's what you end up with. Alright, which is greater, the number of bacteria or the number of all the animals in the table put together? Well, pretty easy to do this here because why? This is 10 to the 30th power. So we're going to go with the bacteria being the largest one. There's no reason to even add all those things up because why? Nothing even gets close to 30. That's 20, but that's the 30th power. That's 10 extra zeros. That's like 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, you even got to go there. That's like 10 million compared to the number 1. So not even close. Okay? So take a moment to do your homework, and then let's pause and check it out. Okay, here we go. Homework time for our last one of this unit. Evaluate the expressions here. Alright, cool. These have the same base. Because of the same base, I can add those together and we can be just fine. So that becomes 10. In this case here, this becomes 10.0 times 10 to the 4th. Now, I can leave it there. We want to give our answer in scientific notation. So that means this has to move to the left. And when that moves to the left, this one goes up. All right. So that becomes 1.0 times 10 to the 5th. Over here, going to do subtraction. Those are the same, so we're okay. So 3.7 minus 3.3 is 0.4 times 10 to the 6. That's less than 1, so we're going to go to the right. When we go right, we go down. Okay, so this becomes what? This becomes 4 times 10 to the 5th. Here, bases are the same, we're okay there. So we're going to add 4.8 plus 6.3, which is 11.1 times 10 to the negative 3. I want to go to the left. Left means this is going to go up. So I'm adding 1, right? Adding 1. Negative 3 plus 1 is negative 2. So I end up with 1.11 times 10 to the negative 2 power. So be careful about that. Here, base is the same. So 6.6 minus 0.1 is 0.5. And right now we're at 10 to the negative 5th. I'm going to go to the right, which means this is going to go down. So going down means what? It means I'm going to subtract 1 more. So that becomes 5 times 10 to the negative, and negative 5 minus 1 is negative 6. Alright, describe a scenario, what's happening in the graph. Number 2, what's happening in the graph? So maybe this is a graph where I have time in minutes and distance kilometers. So here is Johnny, and he's riding his bike at a constant rate, and then he stops at a stop sign and a stoplight, waits for light to change. And he keeps riding his bike for some more minutes, and he stops and takes a little break, and then he starts to ride his bike more, but now he's riding a little faster because it's going a little bit steeper there with that slope. So what is happening at 5 minutes? At 5 minutes right here, we can see that absolutely nothing is happening. Maybe Johnny is taking a little break and pausing on his way home, whatever he's doing, but he's not going any distance. Time is moving on, but his distance is not changing. What does the slope of the line between 6 and 8 minutes mean? Well, between 6 and 8, what I can see here is that he is going, you look at 6, and you look at 7, he's going a distance of 1 kilometer per minute at that point. So he's doing 1 kilometer a minute at that point, which is a much faster, because here he was only doing a half a kilometer a minute. So it's greater than the 1/2 a kilometer a minute he was doing earlier. So he's definitely sped up his game quite a bit there. Alright, number 3. Apples cost $1 each, oranges cost $2 each. You have $10, want to buy 8 pieces of fruit. One graph shows combination of apples and oranges that total $10. The other graph shows combinations of apples and oranges that total to 8 pieces of fruit. Okay, so here's what this looks like here. Mine's not quite as cute as yours because mine is black and white. So let me grab a marker real quick. Okay, so we have the dark ones here. I'm going to make these ones pink just so we can see what's happening. Double things up there. Alright, so I have some pink ones and I have some black ones there. Okay, name one combination of fruit shown on the graph that does not cost $10. Okay, so first of all, for our oranges here, we have oranges and apples all together. You know, apples cost $1 each. We know that's to be the case. So number of apples are $1 each. And if we have $10, we'll buy 8 pieces of fruit. Okay, the graph shows combination. One graph shows combination of apples and oranges, a total of $10. So one is a total of $10 and one is a total of 8 pieces of fruit. So one is $10 and one is 8 pieces of fruit. When we take a look at this here, for the 8 pieces of fruit, how this is going to work out, take a look at how we're going to play this game out. If I had 2 apples, I have 4 oranges there. Or if I look at this one, I have 2 and 6. That there seems to total to 8 pieces of fruit. So this one is my pieces of fruit, where the pink one seems to be my $10 one. Okay, and we're getting information by saying, well, looking at a point, what do I have here? Here's 4 and 4, that equals 8. So name one combination of 8 fruits shown on the graph whose cost does not total $10. Okay, so in this case here, this is my chart of things that are going to be total of 8 pieces of fruit. All the dark ones are 8 pieces of fruit total. Okay, but I want to make sure it doesn't equal $10. $10 is the pink one. So I can actually pick anything as long as it's not one of the ones that's pink. And now this one here is the one where it's pink and dark. Okay, so I could say, for example, I could say 4 apples and 4 oranges. So 4 apples, 4 oranges right here, that amount there is greater than what happens here when it's equal to $10. So that works just fine. Can I pick others? I sure could. Name one combination of fruit shown in the graph whose cost totals to $10 that are not 8 fruits. Okay, so I want $10 that are not 8 fruits. Okay, well, here is a total right here where it's $10 and it's not 8 fruits. Why? $10 is the pink one, so I could say 4 apples and 3 oranges. That's going to be equal to 7 fruits, and it's on a $10 graph, but it's not going to work anywhere else. How many apples do we need to have 8 fruits that cost $10 at the same time? That's going to be this magic point right there. That's going to be 6 apples and 2 oranges. Got it. Alright, and our last one here, and I'm going to call it a day. Alright, solve it and check your equation. So, first thing here, I'm going to distribute. So, negative 2 times 3 is negative 6x. And then negative 2 times a negative 4 is going to be a positive 8. Equals 4 times x is 4x. And then 4 times 3 is 12 plus 6. So we have negative 6x plus 8 equals 4x plus 18. Alright, so I'm going to go ahead, in this case here, let us subtract 4x, subtract 4x, we have negative 10x, and let's subtract 8, so we have over here just a 10. So negative 10x equals 10, divide both sides by negative 10, so x is equal to negative 1. Over here, we're going to go ahead, and what I want to do first of all is I'm going to multiply everything by 2. Why? Well, because I don't like dealing with a fraction. So by multiplying this by 2, that simply goes away. So on this side I'm left with z plus 4. Z plus 4. Oh, first of all, let's do this before I do that. I got ahead of myself. Sorry, I forgot to look at the problem. Let's go ahead and add 6, add 6. So I have 1/2 z plus 4 equals negative 2z plus 14. Now we can go ahead and I can multiply by 2 to both sides. So this goes away. So I have z plus 4 equals, distribute, 2 times negative 2 is negative 4z plus 2 times 14 is 28. Now I can add 4z, so we have 5z over here, equals, and let's subtract 4 equals 24. Divide both sides by 5, and z equals 24 over 5. Weird answer, but the correct answer. And finally over here, let's subtract 4w, so we have 2w over here. Let's subtract 31, so we have equal to negative 38. Divide both sides by 2, and we have a negative 19 equals w. So those are my 3 answers there, and we're done. And it was a great unit, and we'll see you next time.